break.
Okay.
Followed till 12:30, we can handle the class, sir.
Okay. Up to 11 we have session. Then after that we will start by
10
11:10.
minutes. 10 minutes we can take a break.
11:10 to
11:10 to 12:30, sir.
Yeah, that's fine. That's fine.
Thank you, sir. Sir,
Yeah.
our faculty also will be there in the
Yeah,
meet,
please,
sir.
please.
Mr. Uday will coordinate, sir. I will also be there. In case both of us, you can ask us if anything.
Okay. Okay. No issue. No issue. Thank you.
Thank you, sir. Thank you very
Yeah.
much.
Is my screen visible?
Yes, sir.
Yeah, thank you. Yeah, good morning, students, and good morning, faculty. This is Dr. Kiran Kumar. Almost I have 25 years of teaching experience. Especially, I know Dasrath, especially we both teach this comparison for the GATE. So we used to teach during 2010 to 2020, almost all we are in this GATE coaching for this subject compiler design and automata theory and formal languages. These two subjects I used to handle. Of course, I handle almost all 200 plus batches for this compiler design, especially GATE point of view. Okay, but anyhow, we see both all the topics I'll cover, and maybe in the last session we see some GATE questions based on the compiler design subject. Okay, fine. So today agenda is maximum. I don't know your syllabus, but we see this is the course outline. Means what are different topics will be there in this course. Uh, so these are different topics, right? So we see introduction. What is a compiler? And when you say compiler, basically these are the 6 important phases: lexical analysis, syntax analysis, semantic analysis, intermediate code, code optimization, code generation. Okay, any college when they frame the course, so all these 6 phases will be framed into some 5 units or 8 units based on their structure, right? So today's agenda majorly we cover up to lexical analysis. Okay, maybe 3 hours time. I feel maybe plus or minus here and there we cover introduction part and the lexical analysis, which is the first phase of the compiler. Okay, so let us see. Let us start the session without delaying much. Now let us see the basic definition. So what is a compiler? So compiler basically is a program. Okay, it's a program where it translates or converts a source language to its equivalent target language. Then what is source language? Normally, source language or source program normally is a high-level programming language. Could be C or C++, Java, or any programming language. And the target program is an equivalent machine code or relocatable object code. Okay. Or sometimes the target code could be assembly code also. Okay. And during this process, actually, as a user, we majorly feel happy with the error messages that the compiler gives during the execution, because whenever I write a source code, the source code should be written correctly. Okay, so in that process, which will help us means it is compiler, because compiler tells you so and so line number 22, let's say semicolon is missing, or so and so line the parenthesis is missing, or you are using a variable sum, but sum is not defined in case of the C language. So all such errors, okay, the compiler will give us so that we can correct our source code. Okay, so that we can get the required output. So compiler is one where it takes the source program, which is any high-level programming language, and generates equivalent target code. A target code could be a machine code or relocatable code or assembly code also. Okay, and another task that we'll do is, this is first task, and second one is during this process, before it generating target code. Suppose let us say if there are some errors, it gives the errors. Okay, maybe this is first. If there are errors, it shows. And if there are no errors, then it generates the target code. Okay. Yeah, fine. There are basically, we can say, a compiler with two important parts. One is analysis phase, and second one is the synthesis phase. Okay. What is analysis phase? So analysis phase, what we do is we verify the source program in all aspects. Okay, that is lexical analysis. Okay, so anyhow, we see in detail lexical analysis, syntax analysis, and semantic analysis. Okay, so these are the different phases in the analysis phase. And during the synthesis phase, we generate the intermediate code. Then from the intermediate code, of course, we optimize. Then we generate the actual code. Then the actual code also sometimes we optimize. Okay. So the total compiler we divide into two different modules, two major parts: analysis phase and the synthesis phase. So during the analysis phase, what we do? So we verify our source program in all aspects. Okay, we'll see what are different aspects. Okay, but syntactically is written or not, semantically is written or not, whether the lexemes or tokens are generating correctly or not, and so on. Okay. Like, may I know which class you are? Are you in the second year or third year or fourth year?
Third year, sir. 3-1 semester.
Yeah. Yeah. Okay. Thank you. So hope you know like what is lexeme, what is token, but in who we'll discuss that. Yeah. So to give a full picture, these are the different phases of a compiler. So I give input as a source program, and right, lexical analyzer is the first phase, then syntax analyzer, semantic analyzer, then intermediate code, then code optimizer, then code generator. Okay, with that we generate the final machine code, required code, right? And apart from that, there will be two things: error handler and symbol table. Okay, so I just written different. Actually, you can take a symbol table there and error handler module. I just picked this from the website. So all these phases will be connecting to the error module also. Okay, so this is complete picture of a compiler. Okay, so as I told you, I've been telling you since last 2 to 3 minutes. So these are the different phases, 6 phases, right? And these 6 phases will be supported with a symbol table. There is a concept called symbol table. We'll see all these 6. This is complete subject. Okay, this is, we can say this is the big picture of, I can say this is the big picture of compiler. Okay, so what we have in the compiler, I am just putting in one chart. Okay, so complete this 10 hours or 12 hours, we'll be discussing all these things in detail. Okay, fine. Now let us see the first phase. So lexical analyzer. So what is the functionality of the lexical analyzer, or what it will be doing, the lexical analyzer? Okay. So lexical analyzer basically reads source program one character at a time or character by character and returns the tokens of the source program. Okay, for example, what do you mean with tokens? So for example, if you take new value equal to old value plus 12, okay. This is basically, this is the assignment operator in the Pascal or Fortran, but in the case of the C language, this is assignment operator. Okay, do not worry with the syntax. This is assignment operator, but most of you may not be knowing this assignment operator. This assignment operator will be using in the Pascal and Fortran programming language. Okay. So here, what are the tokens means? See here, new value. Okay, new val is an identifier. Okay, so that is considered as one token. Assignment is one token. Assignment operator is one token. Then old value is a variable which is also a token. Okay, then plus is an operator which is meant for addition, is also a token. 12 is a number which is also a token. Okay, so the task of lexical analyzer is, since the lexical analyzer is actually interacting with the source code, right? So it reads one character at a time. The moment it finds the token, it returns the token to the next phase. Okay, so you can take any statement, something like, let's say you say sum equal to a plus b. Okay, so sum is an identifier. Okay, that is a variable, and this is an assignment operator. A is a variable. This is a plus is an operator, and B is a variable. Okay, which is an identifier. Okay, so how many tokens are there? 1, 2, 3, 4, 5. So in this case also there are 5 tokens. Okay, so that main functionality of the lexical analyzer is it reads the source program. It reads the source program character by character and returns the tokens of the source program. Okay, and what are different tokens? all identifiers. All identifiers are token. By the way, what is identifier? Can anyone tell me? What do you mean by identifier? Anyone? What are identifiers when you talk about a programming language? What are identifiers? Identifiers are variable names are comes under identifiers. Okay. Function names, procedure names, right? There are many. Okay, let's say class name. If it is an object-oriented programming, class name or object name. Okay, and so on. So wherever we have a facility to give our own names, all those things comes under identifiers. Okay, so variable names, function name, procedure name, class name, object name, and we have so many like struct name. So in the C language, you have a keyword called structure, where it takes different members of contains different members, may of the same type or different data type. Structure name, uh, uh, array name, I can give any name to an array, right? So I can give any variable name, and so on. Okay, so all these things comes under identifiers. Okay, then right, operators, and this is the number and so on. Okay, now the main functionality of the lexical analyzer is the moment it finds a token, it returns. Second thing is that this information will be fed to the symbol table. Okay, symbol table, I already told you. Symbol table is one module. See, this is a symbol table where it is connecting to almost all the 6 phases, right? So the moment it finds and it maintains the information about each identifier. Okay, especially the symbol table maintains information about identifiers. So then what could be the information it maintains? Suppose if it is a variable, okay. If it is a variable, then what kind of information it maintains in the symbol table? If it is a variable, then what kind of information it maintains? Possibly, what is the name of the variable is one information. What is the type of what is the type of that variable? Then what is the value? Okay, and what is the scope? Or what is the, we have this storage class. What is the storage class? What is the storage class for that variable and so on? Okay. So with the variable, this kind of information will be maintained. Suppose if identifier is a function, if identifier is a function, then with respect to function, what kind of information possibly the symbol table stores? If it is a function, possibly it like what is the name of the function, right? Then uh, how many arguments it is taking? How many arguments, right? How many arguments? Then type of each argument. Then what is the return type and so on. Okay, so if it is a function or a procedure, possibly this kind of information will be maintained as well. Okay, so there are two aspects we discuss as far as lexical analysis is concerned. One is the moment it reads a source program, character by character, the moment it finds a token, it returns that token to the next phase. Second one is if it is an identifier, that information will be feeded, that information will be given to the symbol table, so that other phases they can refer the symbol table, and it may be knowing about what are all these identifiers. Okay, so symbol table, when it's maintaining the information about identifiers, I already told you. If it's a variable, it maintains what is the name of the variable, what is the type of the variable, what is the data type, means data type, right? And what is the value, what is the scope, storage class, and so on. That could be some other information. And with respect to function, what is the name of the function? How many arguments the function is taking? Is it taking one argument or two arguments or three arguments? Then if let's say if there are three arguments, then what is the type of first argument? What is the type of second argument? What is the data type of third argument? Then function possibly may return a value, may not be return a value. So therefore, what is the return type? So all such information will be maintained if the identifier is a function. Okay. right? And basically, hope you are aware, during the recognizing of these tokens, the underlying machine that used by lexical analyzer is finite automata. Hope you are aware what is a finite state automata, right? Finite state machine, you have studied it already in automata theory from formal languages, right? So deterministic finite automata or non-deterministic finite automata, any finite automata will be used by the lexical analyzer, especially in recognizing the tokens. So we'll see, okay, how it recognize, how the finite automata will be designed. For a sample language, we'll discuss. Okay. The next phase is now the agenda is we are going to discuss all these modules briefly first. Then after that we go in detail about the lexical analyzer. So we are discussing. So just now we discussed about the lexical analysis. Now we are discussing about this syntax analysis. Okay, so syntax analysis. So what is this? What is the main purpose of syntax analysis? Okay, so syntax analysis basically it receives the tokens which are generated by the lexical analyzer and it constructs the parse tree. Okay, it constructs the parse tree. Okay. Now, what do you mean by parse tree? How it constructs? That we see completely. We spend, in fact, more time on the syntax analysis. Okay? All this comes under parsing techniques. Basically, there are two types of parsing techniques: top-down parsing and bottom-up parsing technique. And we see. But anyhow, the main theme or main agenda of syntax analyzer is you have written a statement in the source code. Have you written the source code as per the rules of the programming language or not? Because when you write a code in one programming language, let's say you are writing a code in C, okay, and C has some syntax. What do you mean by syntax? The syntax means basically the word syntax means rules of programming language, that particular programming language. Okay. For example, let's say in C language, I say sum equal to num1 plus num2. Okay. And it must be followed by a semicolon. It must be followed by semicolon in case of the C language. Of course, in the Python, the semicolon is not required. So whenever I write a statement, suppose if this is not written, then compiler gives an error telling you that you missed the semicolon. Okay. So in the compiler, from which phase that particular error is coming? That is coming from the syntax analyzer. Hope you are understanding. Okay. So whenever you are write, you can't write of your own choice. Okay. There is some rule. Let's say you write if condition in the C language. I assume that most of you are at least aware of the C language. Okay. Let's say you write a condition in the if condition. Let's say if num mod 2 equal to 0. Okay. So actually this is syntax. You must write in the left parenthesis, right parenthesis, and one condition. Okay. And the left brace and right brace. And if this condition is true, we execute certain statements. Now in this case, suppose let us say you missed this. So it gives you an error. Let's say you missed this and it gives an error. Okay. Or let's say you missed this right brace. So all these are the part of the rules. So if condition, you must write like that only. Okay, here we are writing a condition. Condition is our choice. As per the logic, we write our own condition. But the rules are what? After if, there must be one left parenthesis. It must end with the right parenthesis. And between this left parenthesis, right parenthesis, you should write a condition. And condition may be connected with the multiple operators and so on. Okay. And if it is a compound statements, then it must be put in the braces. Okay, left brace and right brace. Let's say you kept a left brace and right brace is not there, then it is a syntax error. Okay, so basically we see in detail almost all we spend minimum 5 hours on the syntax analyzer. Maybe next Sunday completely we spend on syntax analyzer. Okay, we see all parsing techniques because in compiler design the heart module is syntax analyzer. Okay, and especially for the gate, definitely you find minimum 2 questions from the syntax analyzer. Okay, so therefore we see more time on the syntax analysis. But as what is the main theme of syntax analyzer is, have you written the source program as per the rules of that particular programming language or not? When I say rules, so any programming language contains a collection of rules. when you are writing a for loop, there is a rule. Okay, there is a syntax. Okay, you have to write as per that one. You can't write for loop of your choice. Okay, when you are writing if else, you have to write as per the syntax. If you are writing a normal statement, assignment statement, you have to write as per the rules of the programming language. So whether you followed such rules or not, the syntax analyzer task. If you are not written, then error will be raised. So during that process, the syntax analyzer uses a concept called parse tree. Parse tree. Okay, parse tree, or it is also called as syntax tree. There is small difference. We'll see later. So parse tree and syntax tree. During this process, during syntax analyzer, it uses automata called PDA. What is PDA? Push down automata. Okay, it uses push and automata. Next one is syntax analyzer. Just now I told you, right? So syntax analyzer basically is specified by the context-free grammar. Hope you are aware what is context-free grammar. It is there in the automata then formal languages. And the context-free grammar are mostly recursive. And second one is, next point is syntax analysis checks whether the given program satisfy the rules implied by the context-free grammar. Okay. So in this process, you know that for the context-free grammar, equivalent machine part is PDA, push down automata, right? Yeah, different parsing techniques. I already told you there are two parsing techniques, top-down and bottom-up parsing technique. And the top-down parsing, basically, we are trying to construct the parse tree at the root and proceeding towards the leaves. Okay, so there are different techniques. That means basically the top-down will imitate, there are two derivations, leftmost derivation and rightmost derivation with respect to context-free grammar. Okay, so basically the top-down parsing will imitate or mimic the leftmost derivation. Okay, and some examples of top-down parsing are recursive predictive parsing, non-recursive predictive parsing. Non-recursive predictive parsing is also called as LL parsing. Okay, so this anyhow we'll discuss. This is a very important topic. We'll discuss in detail. And our bottom-up parsing, basically, as a word suggests you, bottom-up means we start with the leaves and gradually we construct and we go up to the root. Okay, basically, the bottom-up parsing technique mimics or imitates the rightmost derivation in reverse. Rightmost derivation in reverse. Okay, I think somewhere else I have written construction of parsing. Yeah. So some of the examples of this bottom-up parsing technique are operator precedence parsing technique. Only it is for the restricted grammar, and LR parsing technique largely we use for the bottom-up. Under LR family, you have under LR you have SLR, you have CLR and LALR. Okay, these are the techniques you have under parsing techniques. Okay, the next one is semantic analyzer. The semantic analyzer basically it checks the meaning of the statement. Okay, whether the syntax wise, rules wise it is correct, and but whether you are written the source code as per the, are you giving a meaning or not? Sometimes maybe whether you realized or not, whether you face the situation or not. Normally, if you write in the C, especially in the C language, I'm telling, if you write A equal to B, okay, let's say you write some code, something like this. Okay, some compilers ignores and it gives output, but some intelligent compilers gives you warning, especially in the C language. Whenever you have warnings, okay, warnings, all warnings basically are generated by the semantic analyzers. That means syntax wise it is okay, there is no issue with the rules, but meaning wise, and some intelligent compilers ask you when you write this, it asks possibly it's not A equal to B, is it A double equal to B or not? Because whenever we are doing this, it means we are checking whether A equal to B or not. So the relational operator is double equal, not the single equal, right? So this is an assignment operator. Assignment operator, what it will do? The right side value is assigned to the left hand side variable. Okay, that is assignment. Okay, so normally in the if condition we check whether these two are equal or not. So the initial days of the C compiler, it used to give an error, which used to give a warning, giving that possibly it is A double equal to V, but you have written A equal to V. Okay. So semantic analyzer basically talks about the meaning of the statement, and especially one of the important tasks that semantic analysis will be doing is type checking. Type checking. That means whenever you are let's dealing with the two different types, or let us say you are taking a string str equal, let's say, Kiran. Then let's say you are taking a variable a which is 12.5. Then you are trying to add this str plus a. So syntax wise, everything is correct. It is an identifier. It is an identifier, and you are adding and you are giving to some result. Syntax wise, it is correct. But meaning wise, you are trying to add. You are trying to add a string with a float value. Okay. So it doesn't make sense, right? You are adding a string with the float, which has no meaning. So therefore, this kind of errors will be raised during the semantic analysis, because there is no problem as far as syntax is concerned. This is as per the syntax only, because left hand side a variable, this is one token assignment operator, this is a variable, and this is another variable you are adding. Let us say semicolon also you have kept in case of the C language. But the problem here is a type. Str is of the type string, and a is of the type, let's say, float. Then you are trying to add a float variable, float value with a string which has no meaning. Okay, so therefore, one main important point to be remembered with respect to semantic analyzer is semantic analyzer checks the meaning of the statement, and especially it will do the type checking concept. Okay, right. Now, next phase is intermediate code generation. So I'll share you this complete PPT after the session. Once I complete, along with this write-up, I'll share you so that you can refer. Okay. Yeah, intermediate code generation. So if you can go back and refer. So syntax analysis and semantic analysis. And we know that these three modules together we call as what? These three analysis phase, right? Analysis phase. Okay, and these three together we call as synthesis phase. And another word is these three we call as front end, and the last three we call as back end also. Okay, for the compiler, front end and back end for the compiler. Okay, now let us see intermediate code generation. This is basically intermediate code generation. So there we see control flow, data flow analysis, and all those things. Therefore, it is mentioned. But otherwise, this module is intermediate code generation. Okay. Fine. So first of all, in the first phase or first module or front end, what you are doing? One is lexical analysis, second one is syntax analysis, third one is semantic analysis. And what we are doing? We are checking the source program in all aspects. Whether when you write int, data type int, you should write int only. You are not supposed to write integer completely. Otherwise, it is not considered as a token. Okay. So that is lexical analysis responsibility. Then have you written the statement as per the rules of the programming language or not? That is the responsibility. Checking that is the responsibility of the syntax analysis. Okay. Then you are written as per the syntax, but have you written the statement by giving meaning or not, whether the types are matching or not? Because whenever you want to add the both should be numbers. Okay, you can add integer with the float, but you cannot add a float with a string. Okay, that is meaningless. So whether you are, that is the meaning by the statement is correct or not, that is done by the semantic analysis. Okay, so once you complete all this checking during these three phases: lexical analysis, syntax analysis, and semantic analysis, then we generate intermediate code. The point here is why you need a intermediate code. Why can't you generate directly a target code? Let's say you verified your source code in all aspects. Then what is the need of generating this intermediate code in between? Okay, I'll tell you the reason. Okay, so once you complete the lexical analyzer, then the semantic analyzer, sorry, syntax analyzer, and semantic analyzer. Then we generate intermediate code. The purpose is intermediate code is basically a platform independent code. Okay, intermediate code is what? It is a architectural neutral, architectural independent code. That means after checking your source code, let us say you want to generate the target code for 3 machines. Let's say machine 1, machine 2, and machine 3. So I want to generate, yeah, any doubt, Chanti? So what we can do is, if you have doubts, there's no issue, you can note down. Maybe I'll just give 10 minutes time during that, 10 or 15 minutes, it's based on your requirement. During that, definitely you can ask all your doubts without hesitation. We'll discuss. Is it fine? Okay. So if I want to generate the target code, for different machines, what do you mean by different machine? Let us say, when I say machine architecture, let's say this could be a 8-bit machine. This could be a 16-bit machine. This may be 32-bit machine. And M1 may have like RISC architecture, reduced instruction set. The instruction set of machine 1 may be different from instruction set of machine 2 or instruction set of machine 3. Okay, so in that case, if I want to derive machine code for different machines, then what we do is initially we generate a machine independent code. Okay, machine independent code. So once you generate a machine independent code, then we optimize the code. Then as per this machine architecture, we generate the target code. And this optimized code again, we generate for the machine 2, for the machine 3. So the main purpose of intermediate code is, whenever I want to generate a target code for more than one machines, okay, then what we do is, before actually generating the target code, I generate a machine independent code, because I don't know what is the architecture of your machine. Okay, so your machine may be 64-bit or 32-bit, or having some set of instructions. So like machine to machine, hope you are aware, computer architecture. Okay, computer architecture, okay, machine to machine, the computer architecture will be different, right? The number of bus lines, number of address lines, everything may be changing. So if you want to generate the machine code as per your machine architecture, then better what we do is, we generate a machine independent code. It is architectural neutral. Okay, and from that we optimize to the possible extent. We optimize, and as per the machine architecture we get. So this is the main purpose of intermediate code. Okay, for example, let's say this is a high level statement. Let's say these are the sequence of tokens that is generated, and then possibly this kind of intermediate code will be generated. We see what are different forms of intermediate code, what are different implementations of intermediate code or not. Okay, so there are almost all 8 forms of intermediate code, and different ways of implementing intermediate code. One is quadruple, we have quadruple, we have triples, and we have indirect triples, and so on. That we'll discuss in detail. Okay, so concluding intermediate code, what is the main purpose of intermediate code is, it is meant for generating a machine independent code. Right? Next one is code optimizer. Okay, the main point here is yeah, fine. Code optimizer. Basically, when you generate the intermediate code, it contains a lot of redundant code. So please make a note of it. Generally, intermediate code, let me write here. Generally, let me write here itself. Generally, intermediate code contains a lot of redundant code. redundant code. Okay, redundant code means what? Repetition of code. That means let us say you have computed some value 4 I and you stored in temporary variable T1. Again, somewhere else after some time, again you compute 4 I, you will be storing in another temporary variable as a T3. Again, some point of time, again you compute 4 I and you will be storing in some temporary variable as a T10. So this happens with the way the intermediate code works, because in the process of generating the machine neutral or architectural neutral code, it simply follows the formula. Whenever you have 4 I, it takes a new temporary variable and stores it. Okay. So, but the point here is, before I generate the machine code, there is no need to generate machine code for this and this and this, because 4 I is already available in the T1. The same T1 I can use here as well as here also, right? Because 4 I is already available in a temporary variable T1. Then what is the need? So, what is a why you go for a code optimizer? Because intermediate code contains a lot of redundant code, so that has to be realized first. And so because of that, we need a code optimizer where this redundant code can be removed. And there are many other techniques under code optimization that we'll discuss in detail. Okay. Then code generation, actually, we generate the code with respect to the machine architecture. Okay. Right. So this is one example. You can find the textbook. Let's say this high level statement, these are the tokens, this is the parse tree, this is the syntax tree, and this is intermediate code and code optimizer, where we are reduce some code, and finally this is the machine code. So this is some example to understand how a particular single statement of the high level language finally it goes and undergo and generates all the this thing. Okay. I just come in 5 minutes. So just please wait. I just take water and. Okay, fine. Am I audible?
Yes, sir.
Yeah, fine. So next one is you have one word called pause. Okay, so earlier we have seen phases, right? So pause means basically a few phases we combine, and that together we call as a pass. Okay? For example, lexical analyzer, syntax analyzer, semantic analyzer, and intermediate code is considered as one pass. Okay, so one pass means what? Lexical analyzer, a syntax analyzer, semantic analyzer, and intermediate code. So pass means it takes the first statement in the source program and generates the intermediate code. Again takes the second statement in the source code, goes through all the phases and generates the intermediate code, and so on. So that means it is in the loops. Let's say source code has 10 lines, assume. So first line, one iteration, second line, another iteration, so on. That is the pass. Okay. So few phases I combine and I form a pass. Okay. And possibly, and intermediate code optimization and code generation will be another pass. Okay. Intermediate code. Once you have intermediate code output, that intermediate code optimization and code generation will be one another pass. Okay, so that it takes intermediate code, it optimizes, generates the target code. Again, goes here, takes the next statement in the intermediate code optimization, so on. So that is the concept of pass. Okay, so there are many compiler construction tools there. You can go through this only literature, nothing great in it. Yeah, now next one is bootstrapping. I don't know whether you have this concept in the syllabus or not, but let me briefly explain what is the bootstrapping. So bootstrapping is a process of generating a new compilers from the existing compilers. Okay. So how we do that? What is bootstrapping? Bootstrapping is generating new compilers from the existing compilers. So let us see that concept. So when you take any compiler, we represent a compiler with a T diagram. Okay, T. S, I, T. This is how we represent diagrammatically. So what is S means? Source language for which the compiler is developed. Okay. So when I say C compiler, so means what here? What is this C refers to? So it is a compiler for the C language. Okay. So the C language refers to the source language for which you are developing a compiler. Okay. Then C compiler, how we implement it. Okay, please make a note. Compiler is what? It is a set of instructions. It is also a program, right? So initial days of when C language just arrived, C compiler is not developed in the C language. C compiler is developed in some other programming language like Pascal, Fortran, and other programming languages. Because by the time C is arrived, people are familiar with the previous programming language. So therefore, so they developed a compiler in other programming language. So please make a note. When I'm developing a compiler for the C, the implementation language for the C may not be the C language. So that is the second component is implementation language. And what is target machine? That means, okay, this is for the so-and-so source program and is implemented in source of programming language. And finally, what is the target machine? Okay, what is the target language it is generating? Okay, so there are three languages. So target machine or with respect to target machine, we generate a code. So therefore, we say this target language or target machine. So any compiler, when you say we represent with a compiler will be associating with the three languages. Source language for which the compiler is developed, implementation language in which the compiler is developed, and T is target machine for which the machine code is generated. Okay, this is a T diagram representation of a compiler. Now let us see what is this bootstrapping is. Bootstrapping is, let's say you have a compiler for the language S implemented in M and generate the machine code for M. Okay. Then this compiler, you are running through this compiler where this is for the language L implemented in S and it works for the machine M. So when you run this through this is 1 and this is 2. When you are running compiler 1 through compiler 2, there is a restriction, these two must be same. These two must be same. Okay, so that's what I mentioned. Implementation language of first compiler. So this is implementation language of first compiler. Must be same as source language of second compiler. So these must be same. Then when you run this first one using or through the second compiler, then you get this as a new compiler. So this is very, very, especially in the, especially whenever the programming languages are evolving. So at some point of time, around, I think, uh, 1940s, I think 1940s, I don't know exactly, but around 1940s, 1950s, like long back story, where almost every year some new programming language is coming. Hope you know the story. Okay, before C language, there is a B language, and before B there is a language, a BCPL language. Okay, so from BCPL, B has come, and with the little changes, C has come, and C has settled for many years. And from that, with the C syntax, C++ is generated, and from C++, Java. Of course, they are completely different, but when you see the syntax wise, they follow the same syntax. The for loop in the C++, for loop in the C, for loop in the Java is same. Okay, so at some point of time, the programming languages are evolving very quickly. This year you have one programming language. Next 2 years we have another programming language, new programming language coming to the market. And whenever there's a programming language, you need compilers, you need interpreters, and so on. And to write the code again, it's a difficult to develop from the scratch. Okay, so this bootstrapping technique helps a lot in generating the new compilers. Okay, so when I have 1 and 2, I can generate 3. Then I can use this, I can run on some other compiler, I can generate another one. So on. So I can, it means within no time, I can generate the new compilers, and I can easily, because this requirement we got whenever the new program nowadays, actually programming languages are not coming that much frequently. Okay, but like way back 50 years back, programming language used to come very, very frequently. Every 2 years or once in a 3 years, a new programming language coming to the market, and there is always a need to develop equivalent compilers for them. So during that process, this bootstrapping is very helpful to the people, where when I have this compiler 1 and compiler 2 and running 1 through 2, of course there is a restriction, these two must be same. When I run, then this new compiler can be generated. So bootstrapping is a process of generating a new compiler from the existing compiler. Of course, there are some restrictions. You can't run any compiler on any other compiler. What is the restriction? The restriction is this. And the new compiler here, whatever you have, the same will come here. Whatever you have, same will come here. Whatever you have, the same will come here by default. Okay. Now cross compiler, another terminology. So cross compiler is one which runs on one machine but produces machine code for other machine. So that is called cross compiler. Okay, now see, it is same. So this is one, and I'm running on 2. I got this. Now see, this is a cross compiler which runs on M but generates the target code for M. These are called is a cross compiler. This is a cross compiler. Okay. Example earlier is Equine is one programming language. After C, actually it has come, and in the compiler for Equine is initially developed in the C language. Okay, and it runs on the machine TRF-OF machines. Okay, there are some machines. Okay, and if suppose if you run this through this, what is this compiler? This is C compiler. Okay, developed on the language. It is Fortran 11. This is 11 means Fortran 11. And it runs like for the machine Fortran 11. So whenever you run this through this, a new compiler is generated. Now see, it is a cross compiler because it is implemented in Fortran 11, but it works for the machine, not for the Fortran 11, but it works for the TROFF. This is another programming language. Okay. So this kind of compilers we call as cross compilers. So cross compilers means what? Which runs on one machine, generates target code for other machines. Okay. Now, some more examples are there, but you see here a two-step process. Okay, so two-step process is what? Let's say initially I have this, and I run 1 to 1. I run the compiler 1 through compiler 2, then this will be generated, right? Because these two should be same, then these two should be same, and this L is coming here, and this N is coming here. And use this, now use this, this is generated. and this one once again I take here. So again, this one I run on the newly generated. I got this new one. Please see this. These two are same. Okay, these two are same. So third compiler is generated. Again, the first compiler I have taken, I have run through this. Then I got this. Okay. So like this, I keep on generate new compilers. Okay. One of the important applications of the bootstrapping is, whenever I have a weak compilers, weakly performed compilers or poor compilers, I can improve the performance by the bootstrapping. Let us say I have this weak compiler. This is weak compiler. So this represents plus represents very poorly coded compiler. Let's say whenever I have this poor compiler and I want to, from this I want basically SMM, which is efficient compiler, where this M plus and M plus represents assume poor compiler. So what I do is I develop this and I run this through this, then this I got. And again, I take this once again here. I run this through 3, then I'll get this 4. Now see, I got a SMM, which is a highly performed compiler. Okay, hope you are clear. The same process, previous process only. Right? So bootstrapping process is used to improve the efficiency of the existing compiler, developing inefficient compilers to efficient compiler. Okay, this is an example. So with that, we are done with different phase of the compiler, and let us see now the lexical analyzer in detail. Yeah. So role of lexical analyzer, basically just now we discussed. So we are done with the initial part. So we discussed all these 6 phases, and of course, symbol table also we discussed to some extent, and error handler module basically handles different types of the errors. So one brief picture of this, all the 6 phases are discussed, and after that we discuss one topic called bootstrapping. Okay, what is bootstrapping? Bootstrapping is a process of generating new compilers from the existing compilers, and bootstrapping is also useful in improving the efficiency of compilers. Okay, so these are the 2 important things. Now let us see in detail about the lexical analysis. Lexical analysis is also called as a scanner. Okay, because it scans the program. Now let us see what is the role of lexical analysis. Of course, we discussed little bit in the discussion. Now we will see in detail. So we know that lexical analysis is the first phase of the compiler, and the main task is what? Reads one character at a time from the source program, right? And generate the tokens as and when it finds. So basically, this is the picture of how lexical analysis works. So it reads the source program, lexical analyzer reads the source program, and whenever it finds token, it gives the tokens to the parser. Once it receives, it asks, get me the next token. The parser asks please send me the next token. So this is something like coroutine. Anyone knows what is coroutine? What is coroutine? Anyone knows? I'll tell you. Coroutine means, let us say there is a function f. There is a code for the function, and function f is calling function g in its code. Then function g is here. It has some code, and somewhere else g is calling f. So in this case, we call here, in this case, we call f and G are coroutines. That means what? Function f is calling G and function G is calling f. Okay, that is coroutine. Now, this lexical analyzer and parser, they work like a coroutine. Okay, they shake hand each other. That means what? Lexical analyzer generates the first token, then it gives to the parser, right? And parser, once it receives, then it asks, okay, send me the next token. Then that means what? Parser is calling. Parser means here it is lexical analyzer. Parser, another name for lexical analyzer is parser. Okay, so once it receives, then it asks, okay, send me the next token. Then it reads the source program and again next generates the next token and so on. So if there are 100 tokens, then every time it gives first token, parser receives the first token and asks the next token and so on. So this loop will iterate for 100 times. And in between, during this process, the symbol table will be interacted, and of course the error handler also will be there. Okay. So they behave like a coroutine. Okay, see here. Upon receiving get next token command from parser, get next token command. This is the command. Then the lexical analyzer reads the input character until it can identify a next token. And once it finds the next token, then it gives that token to the parser. Then parser again tells the lexical analyzer, get me the next token and so on. So this is how it works. And apart from the main task of lexical analyzer is what? It is meant for generating the tokens and giving to the parser with the process of coroutine. The other simple functions of the lexical analyzer is it keep tracks of the line numbers in the source code. Okay, that means what? Let's say this is my C source code. I have written some code in the C language. Then it keeps, let's say, line 1, line 2. Let's say there are some lines of code. So internally it maintains this is 1, this is 2, this is 3, this is 4, 5, 6, 7. So the lexical analyzer internally maintains a file where it maintains a line number for each one. So that is the reason if you are like, if you have an experience in all of you are CSE background. Computer science background only, or do you have touch with any programming language? Okay, fine. So hope I assume you have touch with the programming language. So whenever, let's say in case of the C language, you will get an error something like a line number 6. Okay, let's say parenthesis is missing. You get some message whenever there is an error. So how we are getting this line number 6? Okay, it is because the lexical analyzer functionality is it keeps track of the line numbers in the source code, so that wherever there is error, then that line number along with that statement will be displayed during the error module part, and that will be displayed. And next task is it omits extra spaces and new lines. So that means what? So whenever I write a source code, I give some extra space. Let's say I write F, then I write some code, then function, after that I write function G, and function F to G. For more readability, I may read 2 lines. I read 2 lines, or I leave 2 lines or 1 line. Okay, or whenever I write a statement, something like A equal to B plus C, or instead of writing this, some fellow may write something like A with a space equal to with a space B space plus. Both are correct, but this will have more readability, right? Because whenever there is space, there will not be any confusion. So, but anyhow, these spaces are for the readability, but it doesn't have any role with respect to getting output. So, another functionality of the lexical analyzer is in the source code, wherever you have extra spaces, new lines, that will be removed. The third one is it removes the comments also. Okay, comments means what? So comments means that whenever I write a source program, we write some comments. Okay, right? In the C language, you write a comment something like this. Okay, this is to compute GCD. Some comment I write. Then I write a GCD function here. Okay, I write a GCD function. But this is for what? This is for again readability of the user. Somebody is reading this code, okay, we can understand, okay, this particular function is for computing GCD. But this comment, once again, that it is for the user readability only. It has no role with in getting in the output, right? So all these things will be done by the lexical analyzer. So what are different things that is done by the lexical analyzer? Let me repeat. One is the main functionality is it reads the source program one character at a time and generates the tokens as and when it receives the token. That is one main functionality. And it behaves like a coroutine with respect to a parser. Okay, because this lexical analyzer will call the parser and parser will call the lexical analyzer. And other simple functionalities are it keeps tracks of the line number, omits the extra spaces, new lines, and so on, and removes the comments also. Okay, then what are different issues in the lexical analysis? Okay, especially when combining with the modules. The simpler design is the most important consideration because lexical analysis should be very simple. Then compiler efficiency will be improved and compiler portability is enhanced. Okay, so issues in the lexical analysis when combined with the parser module is, so these are the issues. Compiler portability is enhanced. Okay, and compiler efficiency will need to be improved and simpler design is appreciated. So these are the three things. Now let us say I have been using token. Okay, there are three important terms with respect to a lexical analyzer. One is token, second one is pattern, third one is lexeme. Now let us see what is token, what is lexeme, and what is pattern. Okay, now of course the definitions are there, you can go through it, but you can easily understand here what is token. Now for example, if you see yeah, for example, yeah, if you see this relation, so for all these relation operators, token is relation. We represent the relation, right? And a token could be this is lexeme. Okay, this is token. This is lexeme. Less than is one lexeme. Less than or equal, or assignment operator. Not equal. Greater than equal. So these are different lexemes with respect to the token relation. And there is a pattern. So how we identify the pattern? It is less than or equal, and so on. Okay. For example, you take ID identifier. Okay. So this is pi. Pi is an identifier. Okay. Count is an identifier. You can take, let's say sum is one identifier. So all the variables names are identifiers. So but here with respect to these identifiers, the token is ID. It generates only ID. But these are called lexemes. SUM is one lexeme. Pi is one lexeme. So what is lexeme? Lexeme is a sequence of characters in the source program that is matched by the pattern. That is, this is a pattern matched by the pattern for a token. See, this line gives all 3 points. Right? Now, what is the pattern here? So pattern means for identifiers, there could be some pattern. Can anyone tell me what is the rule for identifiers in the C language? What is the rule for writing the variable names? Can I write a variable something like num1? This is allowed, but one num, this is not allowed. Okay, right? And let us say I cannot take a variable something like let's say principal interest. This is not allowed. Okay, so I cannot use uh, uh, any other symbols only, but let's say principal interest underscore is allowed. This is allowed. Okay, so there are certain rules in there is some pattern. Okay, there is some pattern in taking the variable names. What is that pattern? So initially, it must be a letter. Okay, and letter can be followed by a letter or a digit. Okay, so this is one pattern. Okay, letter followed by letter or digit is a pattern. For that we use a regular expression to represent that. Okay, using that regular expression, we write the patterns. Okay, now lexical analyzer basically there are three important keywords. Let me summarize. One is token, second one is pattern, and third one is lexeme. What is lexeme? Lexeme is a sequence of characters. So here in this case, count is a sequence of characters C-O-U and D. Okay, in the source program that is matched by the pattern. See, this is matched by this pattern, and for a token. And what is the token? For all these things, the token will be ID only because they comes under identifiers. Okay, so for specifying the patterns, we use regular expressions. Okay, so input buffering, all these things are there. Then recognition of tokens. So how the token will be recognized. Okay, so I already told you, for example, if there is a pattern, then letter, let's say the pattern for the variable is initiated with any letter followed by letter or digit. Okay, then we write something like this. Okay, and for the num, it is digit plus. What is digit plus? And what is digit? When I say digit, it could be any digit from 0 to 9. And digit plus means you out of this 0 to 9, you can take like you take any digits and repeat. Okay, for example, 200 and 200148 is a number, right? Because I have taken 2, then 1, and 4, then 8. So this is the hope you know the regular expressions. Okay, this is a regular expression for the number. Okay. Yeah, now let us see a simple case. This is the grammar for it. This is a grammar for if-else statement. This is if expression then statement. This is for simple if. This is for the simple if. This is for if-else. Okay. And see, statement is if expression then statement. Okay. Or if expression then statement, else statement. Or epsilon statement could be null. Then what is expression? Expression could be a term, a relational operator, a term, or a simple term. And what is term? Term could be an ID or number. So this is a grammar. Okay. Now we use this grammar also. Now, and delimiter, when I say delimiter could be a blank or a tab or a new space. And white space. White space is what? White space is a delimiter plus. So delimiter you take more, then that is white space. Okay, now let us see the regular expressions patterns for the tokens. Okay, let's say white space, there is no token for it. For the if is a token. For then is the token. For the else is the token. For the identifier, ID is the token, and attribute, it will be an entry will be making the symbol type, right? For num is token, and for number also it will be making the symbol type. These are the relational operators. Now how the tokens will be generated, see here. So this is the finite automata for the relational operators, how it recognizes a different relational operators. So we design a finite automata this time. So we start here. Let's say the symbol is let's say less than or equal. So less than or equal means what? So it comes here first start. So less than is here. So then after less than, you have equal here. So you come to the final state. Hope you know this is a final state. And you are returning what? You are returning relational operator. That what is that? It is less than or equal. Okay. Let us say it is greater than or equal. Then how you come here? This is a start. This is less than, so therefore not this path. This is equal, not this path. So we go in this path. Then after that you have two paths. Here you have equal. So you come to the final state. This is the final state, right? And you are returning a token called the relational operator, and specifically what kind of relational operator? It is greater than or equal. So this is how we design finite automata in recognizing the tokens. So finite automata is used during lexical analysis phase. Please make a note of it. Not only less than or equal, it is for all tokens. Okay, now let us say I want to identify the identifiers. So identifier, what is the regular expression for the identifiers? What is the regular expression? It is a letter followed by a letter or digit, whole star. So star means what? Repetition of this part, 0 or more number of times, right? 0 or more number of times. And how we design a finite automata for this? So you take a start initially. And what is letter here, by the way? What is letter? So letter could be A or B or C or Z or small a, small b, or small z. What is digit? A digit could be a 0 or 1 or 2 or so on up to 9. Okay. So letter, initially it should be letter. Then it could be a letter or digit. Since it is star, even this can be omitted. Single letter is also fine. Then other means what? Other could be a delimiter. There's a space. Then you come to the final state and assume that an identifier is returned. And for the number, the regular expression is what? Digit plus, right? For the number, the regular expression is digit plus. So digit, we already discussed. Therefore, it is digit, one digit, then followed by any number of digits. Then once you have a delimiter, then you halt and say it is a number. Okay, this is how we design automata, so that this automata will be helpful in recognizing identifiers, in recognizing numbers, in recognizing operators, and so on. So lexical analyzer completely uses this finite automata in generating the tokens. Okay. Now let us see another topic with respect to lexical analyzer, that is scanner. Okay. So in the early days of compilers, we don't have automated tools for generating the lexical analyzers. Okay, but later versions, even lexical analyzers can be generated automatically. Okay, so automatically means it's not the magic, right? So in the magic, suddenly out of hands, we can bring a bird. Okay, so automatic means automatic also needs some input, right? Let's say you go for ATM. Okay, ATM is automatic teller machine. Automatic. ATM is automatic, but automatic means it is not a God given machine. So when you go to the ATM, give me 1,000, it will not give, right? So ATM also needs some inputs. What are the inputs? You need to insert a card, and actually you should have account. You should have amount in your account. Then you enter your password. Then you say withdrawal. There should be some process. There should be some input. Then cash should be there in the ATM machine, and amount should be there in your account. Then only that automatic process will done. Similarly, right? Even similarly, let's say automatic coffee vending machine. Okay, so for the automatic coffee vending machine, it will not come coffee just like that. If you on, coffee will not come. What is the inputs required? You should pour coffee powder, milk powder, maybe water, all ingredients you have to put into that machine. Then you start, you say on, then maybe it give you a cup of coffee. So automatic, though it is automatic, it also needs certain inputs. Okay. So now let us see this Lex tool. What is this Lex tool is? Lex tool is used to generate the lexical analyzer automatically. I just now told you, automatically means it will not happen just like that. For this also you need certain inputs. So how you generate means, in the step one, we write a source code called lex.l, very simpler programming language, where you can easily write down this code. Okay, where this lex.l we write all the rules of the programming language. Then there is a compiler called Lex compiler. Okay, in case of the Linux platform, you can have Flex. You have Flex. Okay, I think you have one more. Different flavors are there. So you can easily practice this Lex programming also. If you are really interested, you can practice Lex programming. Okay. So this lex.l source code we write, then we compile through Lex compiler. Then it gives you output as lex.yy.c. You can see this particular file will be generated once it is successful. Then after that, this lex.yy.c, please see the extension, it is C. That means what? It is a C file. It is a C file. So this C file, you compile using C compiler. Am I right? C file you should run through C compiler only. Then you get an output file at a.out. A.out, you know that in case of the Linux platform, all the C languages, if it runs successfully, it generates an output file called a.out. And this a.output, when you run, you give the input, it gives you sequence of tokens as output. Okay. So this is how this Lex tool works. Lex tool is meant for generating lexical analyzer automatically, but anyhow, there is one input required. You have to develop this Lex source program. Once you develop this, then your task is done. You run through Lex compiler, this will be generated. Then this you run through this, you will get an output, and that output you run it, give required input, it gives you sequence of tokens. Okay. And let us see what is this Lex source program. What is the format of this Lex source program? So Lex source program basically contains three parts: all the declarations, variable declarations and other declarations, and this is a part of the syntax. And the second part is translation rules. That means this is part one, this is part two. Just to indicate that it's part one, part two, we separate with this 2% symbols. It is a part of the syntax of Lex. Okay, then I write all the translation rules. Well, that means whenever this particular pattern is found, then what action I should take and so on. Then for the action part, we use some auxiliary procedures. That means some functions we write here. So any Lex program typically contains this structure. Initially, even C language also. The C language also, what is the structure? As per your knowledge, tell me, C language. Initially, you will be having all declarations, right? I say int A comma B comma C, right? All the declarations will be there. There could be some statements. Then there could be some methods, right? F method, F function, G function, and so on. Maybe these functions can be called in the main method. Okay, so more or less same structure for the Lex program also. Initially, I will be having all the declaration part, then all the translation rules and auxiliary procedures. So these are the three parts, and these three parts will be separating with these 2% symbols. Okay, then what is this declaration consisting of? I just now told you. Declaration of a variable constants will be there. And the translation rules, basically this is the structure. There will be some patterns. So here, what is pattern? Pattern means, in this context, it is a regular expression. Pattern is nothing but a regular expression. Okay. So whenever this pattern is found, then I need to perform this action. If pattern 2 is found, then this action need to be performed. If pattern n is found, then this action need to be performed. So translation rules is of the form PI action I, which indicates that for each PI, the regular expression, the action I represents what? action to be taken when there is a pattern PI is found. When the pattern when when the pattern when the pattern PI is found. Okay. Yeah, fine. We'll take a break. Yeah, one last slide. So this is an example. This is an example one. Example code where you can see last slide. Sorry. So we have all declarations here, right? All these are declarations. What is delimiter? Letter means these are the letter, these are digits. So this is declaration part. And then you have translation rules. So a typical Lex code will be looking like this. Okay, white space if and if this pattern is found, what you have to do. If this pattern is found, what you have to do. Okay. Then these are the methods. Some methods required for this. Okay. So this is the typical structure of Lex, where it is useful for generating tokens for relational operators, identifiers, constants, and yeah, that's all. Okay. So this is a source. This is the Lex program. This is the Lex program. Okay. So with this, we are done with the first module. I will take a short break for 10 minutes as your principal suggested. And around 11:10, we join. Okay. Yeah, thank you all. Yeah, fine. We'll continue the session. I have shared you the Unit 1 PPT. That Unit 1 actually as per our syllabus, more or less, I think for you also the same kind of contents will be there. Fine. So we'll continue discussing the second one. Okay. So first phase is over, right? What is the first phase? Lexical analyzer, right? So lexical analyzer is over. Now let us see the other part. Yeah. Is my screen visible? Anyone please respond once. Am I audible? Yeah, okay, right. Fine, fine. So this, one minute. Yeah. So lexical analyzer we discussed in the morning slot. Now let us see the syntax analyzer part. Okay. Yeah, fine. We already discussed in the morning for the syntax analysis, we use the context-free grammar. So let us see some basics of what is the context-free grammar. Basically, context-free grammar is a four tuple VTPS. Hope you are aware. You are already studied in formal language and automated theory subject. Or I don't know how you call it. Either you call as a formal language and automated theory or theory of computation. That subject name. Different universities will call the different names. So context-free grammar is basically four tuple VTPS, where V is set of variables, T set of kernels, and S in V is a start variable, right? And P set of fractions of the form A to alpha. And what is A? A is any single variable, and alpha belongs to V plus T whole star. What is this V plus T whole star means? V plus T whole star means what is V? V is variables. What is T? T is terminals. And when you say V plus T whole star means it is any string. This means any string with variables and terminals. Okay. Now let us see one example grammar. Now if you see, this is the context-free grammar for representing arithmetic expressions, okay, which containing the operators, only two operators, plus and star. Something like ID plus ID star ID. Okay, or something like expressions. Let's say A plus B star C, or A star B minus star plus D. Okay, so this is the context-free grammar. And if you want the parenthesis, okay, let us say instead of this, if you want to give more priority to the plus, you can use the parenthesis also. So this is the context-free grammar which generates what kind of strings it generates. It generates any arithmetic expression, but containing only two arithmetic operators, plus and star, including the parenthesis. Okay. And now let us see some terminology, important terminology with respect to this leftmost derivation, rightmost derivation, and the parse tree. So let's consider this string ID star ID plus ID. And with respect to the previous grammar, what is the grammar? The grammar is e to e plus t or e to t, t to t star f or f, f to left parenthesis e right parenthesis or id. This is the grammar. Now with respect to this grammar, and of course here e is the start variable, right? E is the start variable. Because any string, if you want to derive, we have to start with the start variable only. Now I want to derive this string. Now let us see how we do that. There are many ways. One way is you can do leftmost derivation, or you can do rightmost derivation. Okay, and based on this, you can construct the parts tree also. Now let us see this. So how I do this? One possible way is I take the production initially e to t. Okay, I take e to t. Then t has two productions, right? T to t star f and t to f. So I just taken this t to t star f. Now the leftmost derivation means in the leftmost derivation always use leftmost variable for expansion. Always use leftmost variable for the expansion. Okay, that means here you have two variables, right? T and f. In these two, what is the leftmost variable? T is the leftmost variable. So you must use this variable to expand further. So therefore, for this, what production you use? This production you use. So in place T to f. So therefore, in place of T, f is replaced. Again, there are two variables. Okay, and I must expand this only. Now, what is suitable production? F2 ID. F2 ID is selected. So that I got this ID. So every time we see this. Then I have star, fine, no issue. Then I want parenthesis. From F, I want parenthesis means what is suitable production? This is a suitable production. F2, left parenthesis, E, right parenthesis. So therefore, we selected this. So if we selected this, so in place of F, I can take this left parenthesis, E, right parenthesis. Now, in place of E, what is the suitable production? Because I want ID plus ID. So, if you want plus from E, this is the suitable one. So, therefore, E to E plus T, this particular production is selected, right? Then in place of E, E plus T is taken. Now, again, here we have two variables, E and T. And in this, what is the leftmost one? E is the leftmost one. So, please make a note in the leftmost derivation. We should always use the leftmost variable for the expansion for the next step. Okay. So E, what is suitable production? E to T, right? So you take E to T. Then you have two variables, T and T. This is the leftmost one. The suitable production is this, right? T to F. So therefore you take this. Then again, F and T, there are two variables on the left hand side. In the, like we have two variables, and this is the leftmost one. F is the leftmost one. And since I want ID from F, so therefore obviously this is the suitable production. So therefore F to ID is selected, and so on. Okay. So ultimately, uh, the is generated. Okay. Derivation of a string. Specifically, we follow the leftmost derivation. That means at each step, we expanded the leftmost variable only. Okay. So this kind of derivation we call as leftmost derivation. Why we are discussing? Because I already told you, when parsing techniques, there are two parsing techniques. Okay. What are the two parsing techniques? Top-down parsing and bottom-up parsing, right? Bottom-up parsing. Top-down parsing basically imitates the leftmost derivation. Top-down parsing basically imitates the leftmost derivation, and the bottom-up parsing imitates rightmost derivation in reverse. It imitates what? Rightmost derivation in reversal. That is the reason we should know what is leftmost derivation, what is the rightmost derivation. Okay. So this is all about how you derive a string using leftmost derivation with respect to a particular grammar. Now let us see how you do the rightmost derivation. Okay, for the same string, and of course the grammar is once again same. So the grammar is same grammar and the string is same string I have taken. The grammar is E2 E plus T T T2 T star F R F F2 left parenthesis E. Fine. So it is again how you do this. Okay, ID star ID plus ID. So initially I take E2 T production. Then in place of T I choose this T2 T star F. Okay. Then since it is the rightmost derivation, we should always expand the rightmost derivation. That is important. So therefore, in place of this F, now T and F, there are two variables here. Okay. So in this, we call this as what? All these things we call as sentential forms. Right sentential forms. Okay. This is one sentential form. This is another sentential form. This is a terminal, another sentential form, and so on. So during the process of getting the required string, we apply different steps. So all these things we call as a sentential forms. Okay. So in this sentential form, T star F, now F is the rightmost one, right? F is the rightmost one. So since I am talking about rightmost derivation, this F has to be expanded. So for the F, what is the suitable one? So because from F, I want this left parenthesis, therefore we use this. Okay, now again we have two variables, T is there and E is there. And since we are following rightmost derivation, E has to be expanded. Therefore, we selected this, then now see there are three variables, T is there, E is there, and T is there. And this is the rightmost one. So therefore, for that, we have selected this T2F. So therefore, T2F is written. Okay. Now again, three variables, T, E, F. So this is the rightmost one. So therefore, F2 ID is selected. Right. Now we have two, E, T, and E. And this is the rightmost one. So therefore, as per this production, E2T is selected. Right. Now there are two variables. This is the rightmost one. So in place of this is selected. Right. Now again there are two variables T and F. In place of this F, this is selected. So therefore this. So like that. Okay. We just see the required string and the possibilities and finally derive it. Okay. Fine. Yeah. So this is rightmost derivation for the same string using the same grammar. And now let us see the parse tree. So this is the parse tree. So parse tree we can easily construct by referring either the leftmost derivation or the rightmost derivation. Okay. See, this is the leftmost derivation, right? This is the leftmost derivation. In the same way, we can construct the parse tree. So initially, we selected E2T, right? We selected E2T, right? Let me write how we can construct this. This is the grammar E2E plus T R T T2 T star F R F F2 left parenthesis C R ID. And what is the string here? ID star ID plus ID is a string. Now, what is the leftmost derivation for this? What is the leftmost derivation for this? So initially we are taken E to T. Then in place of T, we are taken T star F. And in place of here T, we are taken F. So F star F. Then in place of this F, we are taken ID star F. Then in place of this is the leftmost derivation. I'm writing again for you. left parenthesis E, right parenthesis. Then in place of this E, we have taken E plus T, and ID star, in place of E, we have taken E to T, so T plus T. Again, this is the leftmost one, ID star F plus T, because T to F is the production. Then ID star ID plus T. Now here there is only one variable, now that has to be expanded. So ID star ID plus T to F. And finally, the required string ID star ID plus ID. So in fact, this is the leftmost derivation. Okay, now once you have leftmost derivation, we can easily construct the parts tree using this. See, initially this is E to T, so E to T is taken. Now, in place of T, what is taken? T to T star F. So therefore, in place of T, it is T star F. Okay. Now, in place of this T, what is taken? F. So therefore, F is taken. In place of F, ID is taken, right? Then this is the F. In place of this F, what is taken? Left parenthesis, E, right parenthesis. Therefore, in place of F, left parenthesis, E, right parenthesis is taken, right? And so on. Okay. And in place of this E again, E plus T is taken. So E plus T, and E to T, T to F and ID, and T to F and ID. So either you refer leftmost derivation or you refer rightmost derivation, you construct the path tree. So this is all about how you write a leftmost derivation, rightmost derivation, or a parse tree for a string with respect to a grammar. Okay. And yeah, in this context, there is one important thing called ambiguous grammar. So when you say that a grammar is ambiguous grammar, okay, so we say that a context-free grammar is ambiguous if there exists more than one leftmost derivation for a string, okay, or if there exists more than one rightmost derivation for a string, or if there exists more than one parse tree for a string. So these three are equivalent definitions, okay. If there exists more than one leftmost derivation, it is ambiguous, or if there exists more than one rightmost derivation, it is ambiguous, or if there exists more than one parse tree, it is ambiguous, okay. But please make a note that, please make note that given a context-free grammar, whether that is ambiguous grammar or not, so that problem is undecidable, okay. What is the problem that is undecidable? Whether I mentioned or not, let me write. Yeah, it's not mentioned, but let me write here, okay. What is that? Note. Given a context-free grammar, to find whether that CFG is ambiguous or not. So this problem, it is undecidable. This problem is undecidable problem. That means what? There is no algorithm existing. Okay, you should go for applying trial and error methods. Okay, try to have one leftmost derivation, and you just check alternatively whether you can have more than another, like one more leftmost derivation or not. When there are two leftmost derivations, then obviously correspondingly you have two parse trees. Correspondingly, you will have two rightmost derivations. Okay, so this problem basically given a context-free grammar, whether that is ambiguous grammar or not, there is no algorithm existing as of today. But that is the reason it is called, this problem is undecidable. Okay. Now let us see. Just now I told you it is undecidable, but we can try with a trial and error. Suppose if you take this grammar, what is the variable here? The variable, there is only one variable. That is this. What are the terminals in this? The terminals are A and B. And of course, since there is only one variable, this itself is a start variable, and these are the productions. How many productions are there? There are three productions, 1, 2, and 3. Now we consider the string AB and see whether there exists more than one leftmost derivation for it or not, or check whether it is ambiguous or not. Can you try this, anyone? Let me see. Just wait for 1 minute. Let me know, since there are many participants. I'll give 1 minute time and tell me, let me know whether it's ambiguous or not. Just try if there exists more than one leftmost derivation. Anyone from this class? Is it ambiguous or not? Okay, fine. Now see here, it has the two leftmost derivations. Okay, or two parse trees. Okay, one is the grammar is what? S2 AS BS is one production. Second one is BS is and the production are epsilon. So one way is I can take the leftmost derivation. I can take S2 AS BS. I can start with this. Then in place of this particular S, I can take epsilon. So therefore it becomes AB. Yes. And in place of this S, I can take A, B, and I can take once again A, S, B, S. Now this is the leftmost one. So A, B, A, B, S. And in place of this also I substitute epsilon. So A, B, A. So this is one leftmost derivation possible. So that is how the same parse tree is shown here. Now another possibility is I start with initially AS, BS only. So step 1 is same, but see the step 2. In place of this leftmost S, now I'm using BS AS, and this BS is as it is. Now total there are 3 variables, and this is the leftmost one, right? So in place of this S, you substitute epsilon. You substitute epsilon here, then I get ABA, S, BS. Now this is the leftmost one. Again, here also we substitute epsilon. We get AB, ABS. Again, here also we substitute epsilon. So AB, AB. And corresponding to this, this is the parse tree. So there are 2 leftmost derivations. Hence, of course, when you have 2 leftmost derivations, equivalently we will be having 2 parse trees. Okay, and of course we will be having 2 rightmost derivations also. Anyhow, so what is the conclusion? What is the conclusion? Conclusion is given grammar, given context-free grammar is ambiguous. Okay. Now let us see left factoring grammar. Let us see some definitions of left factoring grammar. So what is this left factoring grammar? Okay, let's see the definition. A context-free grammar is said to be left factoring grammar if it contains productions of the form A2 alpha beta, A2 alpha beta, or A2 alpha gamma. So here A has 2 productions. One production is of the form alpha beta. Second production is of the form alpha to gamma, alpha gamma. Now, why it is called left factoring means, now see the first production. This is the first production. This is second production. In both the productions, some part is common. That alpha part is common on the left hand side. So whenever you have this kind of productions, we call this as a left factoring grammar. Now all of a sudden, why you are studying this all left factoring grammar? Because left factoring grammar is a troublesome for the top-down parsing technique. So that is the reason we are discussing all the required terminology with respect to the context-free grammar. Okay, so this is a troublesome. We cannot directly construct a parse tree for the or parsing table for the left factoring grammar. Okay, so that is the reason we are studying what is left factoring grammar. Then we also study what is left recursive grammar and so on. Okay, so is it clear what is left factoring grammar? Whenever I have a production of the form A to alpha beta or alpha gamma, it means some part in the beginning for the both production is common. Alpha is common in the both productions. So therefore, this is a left factoring grammar. Okay, fine. Now let's take an example. Now if you take this is for if expression. So statement for the if else structure. So if expression then statement. IETS means if expression then statement, which is nothing but a simple if. Okay, and this is if expression then statement else statement, which is for if else. Okay, and a statement could be any atomic statement, and expression could be any condition. Okay, now if we see this grammar, this is basically a left factoring grammar. Why it is left factoring grammar? See these two productions. In these two productions, some part is common. What is that part is common? IETS is common here. Here also IETS is common. Okay. So that means what? Suppose if this is alpha, what is beta? Beta is not there. So beta is something like epsilon. So this is alpha, and here this is gamma. So both the productions are starting with the same substring. So we call such grammar, such CFG as a left factoring CFG. Okay. Now we don't require that, especially when you want to construct a top-down parsing for a grammar, and if it contains left factoring, we can't directly go with that. We need to remove, or we need to find out equivalent context-free grammar without a left factoring. Okay. Now let us see what is the procedure, how you remove or how you obtain equivalent grammar without left factoring. Okay, fine. Now see this. Let us say whenever you have, these are basic concept. Whenever you have a left factoring of this form A to alpha, beta, alpha, where this alpha is common part. That means in the derivation process, from A, I want alpha. Now the confusion here is, if you want alpha from A, then there are two productions. So that is this leads to ambiguous. So then, if I want alpha from the A, so shall I choose the first production or the second production? Am I right? So it's a ambiguous thing. So therefore, that is the reason this kind of productions are not encouraged, or we need to remove left factoring in the given context-free grammar. Then we proceed with the construction of a top-down parsing table. Okay. Now, the equivalent grammar is something like this. So A to alpha, because alpha is common, then you take a new variable A dash. So here A dash is a new variable. A dash is a new variable. Okay. So we just take a new variable, then alpha to A dash. And from A dash, either you can choose beta or gamma. So it's something like this. Let us say you are here. Okay, and there is a point here, and from here there are two ways. Okay, so this is one place. Let us say this is another place, and another place. Right now, when you are here, now either you can go in this way or in this way. So to avoid the confusion, first you come here. Once you reach here, then you decide. If you want to go, then you go like this. Or if you want to go, you can go like this. But sitting here, if you want this route, then whether to choose this path or this path is difficult thing. So therefore, you come here, then you decide. So that is the point. So A2 alpha is common, then followed by A dash. Then once you get alpha, then after alpha, whether you want beta or gamma, for that you from A dash you decide beta or gamma. That is how we find the equivalent grammar. So please remember this as a formula. So whenever you want to remove left factoring from the given grammar, we apply this formula. Now let us take this. We know this is a left factoring, right? This is a left factoring. Now if you apply this formula, now this is C, this is alpha, just now I told you. IETS is alpha. In this case, beta is not there. Beta is not there means what? Beta is epsilon. And in place of gamma, we have ES. Okay, and remaining S2A, there is no issue. S2A, there is no issue. E2B, there is no issue. We can take it as it is. So as per the formula, whenever you have A2 alpha, beta, alpha, gamma, what you have to take? S2 or A2 alpha E dash. So see, that is the reason. What is alpha here? IETS is alpha. So I have taken alpha, then followed by some new variable. So since it is the variable is S, I have taken S dash. So here S dash is a new variable. S dash is a new variable. Okay. Then this S2A is as it is. There is no much confusion with this. So we take S2A as it is. Then A dash to beta or gamma. What is beta in this case? Beta is epsilon. What is gamma? Gamma is ES. Therefore, S dash to epsilon or ES. Then this E to B is as it is. Okay. So see this. This is the equivalent grammar. This is the equivalent grammar without left factoring. Right? This is the equivalent grammar without left factoring. Right? Now let us say one more grammar, a specific grammar called left recursive grammar. Left recursion. So this left factoring and left recursion creates a confusion, especially when we construct a top-down passing technique, because top-down passing technique imitates leftmost derivation. Okay, so with leftmost derivation, this left factoring and left recursion obviously creates some confusion. So let us see. First of all, step one is what is left recursive grammar, and the step two is okay. Once the given grammar is left recursive grammar, then how you obtain the equivalent grammar without left recursion. So let us discuss these 2 points. Okay. Fine. Let us see the definition first. What is left recursive grammar? Any context-free grammar is said to be left recursive grammar if it contains productions of the form A to A alpha. Okay. Now here, what is the thing you need to observe? See, it is a production of the A, right? It is a production of the A, and A variable on the right hand side. See, again starting with A. So this kind of what is alpha here? Alpha could be anything. Alpha belongs to V plus T whole star. It could be any string. It could be any string with variables internal. That doesn't matter. But A variable productions on the right hand side, again, if it is starting with A, so such kind of context-free grammar, such kind of productions, we call as left recursive production. So it is a confusion. So how many times I should take this here? So this has to be removed. Okay. Now let us, for example, you see this. Already we consider this. So this is a left recursive grammar. Why? See here, E production on the right hand side again starting with E. Right? This is something like alpha. Right? So alpha could be any string, but E production at the beginning starting with E. That is left. Similarly, not only that. If you see the T production, especially the first one, T production on the right hand side again starting with the T. Okay, and after that we have some string alpha. Okay, so this kind of strings, this kind of productions are called left recursive productions. And if you have left recursive production, the grammar we call it as a left recursive grammar. Okay. and this is also not encouraged. This is also not encouraged. We need to remove this left recursion from the given grammar, especially in the context of constructing top-down parsing table. Okay, now let us see how we remove this. Removing left recursion. So let us say you have a production of the form A to A alpha beta, where beta is not starting with A, where beta is not starting with A. Okay, so in that case, how you get the equivalent constructive grammar is, okay, so A to beta A dash, that means this is A, right? This A to beta, and you introduce a new variable. Here, what is A dash? Here, A dash is a new variable. A dash is a new variable. Okay, so the productions which are not involving in the left recursion, that is A to beta, you add a new variable. Then from new variable A dash to this alpha part A dash and epsilon. So this is a simple rule to remove the left recursion. Okay. In general, let us say this is only for two products. Let us say you have a grammar of the form A to A alpha 1, A alpha 2, and so on, A alpha n, followed by beta 1, beta 2, and so on, beta k, where all this beta 1, beta 2, beta k are not starting with the A. Okay, so whenever you have this, and the equivalent grammar is what? A to beta 1 A dash. This is most general formula. Beta 2 A dash, and so on, beta k A dash. And what is A dash productions? A dash to alpha 1 A dash, alpha 2 A dash, and so on, alpha n A dash, and finally epsilon. So this is most general, because there may not be always one production which is involving in the left recursion, and there is only one production which is not involving in left recursion. There could be some n productions which are involving in left recursion. There are some k productions where n and k are more than one, okay, or greater than or equal to one. There are some k productions which are not involved in left recursion. In that case, how you obtain the equivalent grammar without left recursion? So this is the formula. So for all those productions which are not involving the left recursion, you take it as it is, and at the end you add a new variable, let's say A dash. And the A dash productions are what? A dash to what are the productions that are involving the left recursion? You pick the alpha part. So that is alpha 1 A dash, and alpha 2 A dash, so on, alpha n A dash, and finally epsilon. This is the most general one. This is a simple one where there is only one production involved left recursion, and one production that doesn't involve left recursion. Okay. Now let's take the same example. So this example, so these are the form A, this is A, and this is alpha, and this is beta, right? Now as per the formula, what you get? It is A to beta A dash, that is E to T E dash, right? And A dash fractions are what? A dash to alpha A dash. In this case here, in place of A, I have E, and what is alpha in this case? Plus T is alpha. Okay, now see this answer. So if this is the grammar, yeah. So for this grammar, see this. I have to take one second here. Let me take this. So this is something like A, this is A, and this is alpha, and this is beta. Now, as per this formula, it is A to beta A dash. So therefore, E to this is beta E dash. Then what are E dash productions? E dash productions are E dash to this is alpha part plus T E dash and epsilon. Similarly, this also this is in place of A I have T, and in place of alpha I have star F, and in place of beta in this case I have F. Applying same formula, we will get this. And with respect to F productions, there is no issue. Okay, there is no left recursion, therefore F productions are taken as two. So altogether, for this context free grammar, which is a left recursive grammar, the equivalent context free grammar is this. Okay. Yeah. Now let us start discussing. Once you are thorough with this left recursion, left factoring, leftmost derivation, rightmost derivation, parse tree. Now let us see what are different types of parsing techniques we have. So we already discussed in the morning slot. Basically, parsing there are two types. One is top-down parsing. Second one is bottom-up parsing, right? So under top-down parsing, there are two things: recursive descent parser and non-recursive predictive parser is also called as LL1 parser. So this is very important part where this is very basic one. This is very basic one. Okay. And which is very inefficient also. We don't normally do that. Okay. In the beginning days of compiler, when we don't have efficient parsing like LL and SLR, we used to do that with a simple languages. It is useful. Okay. Now under bottom up, we have one is shift radius parsing. This is the most general. This is most general bottom up parsing technique. And specific techniques are LR techniques are there, and under that you have simple LR, canonical LR, and look ahead LR. Okay, what is S refers to? Simple LR, canonical LR, and look ahead LR. Okay, so these are different techniques. So with this complete parsing techniques we covered here. Okay, and of course under bottom up parsing technique we have one more called operator precedence parsing. This is also bottom up parsing technique, but it is specifically implementing the precedence and association or associativity in the arithmetic expression. Okay, we'll see all those things. Yeah. Now let us see the first one. This LL parsing. Okay, LL parsing are predictive or non-recursive predictive parser or LL parser. First of all, what is this LL? I think I didn't mention LL anywhere. Nowhere. Yeah. LL means LL1 or LL means it is left to right scanning or reading, scanning or reading of the input by imitating leftmost derivation. So first L is the first in the left to right, that is that. Then second L is this with one look ahead symbol. One look ahead symbol, and normally LL1 we can also write as simply LL. By default, we see one symbol, then only we decide. Okay, with one look ahead symbol. Okay, so this is overall picture of how this predictive parsing algorithm or complete predictive parsing works. Okay, so you have a a parsing program or parsing algorithm, predictive parsing or LL parsing, then it need two things. One is the stack and second one is the parsing table. Okay, so before you proceed to parse, you need to construct the parsing table. Okay, once you construct the parsing table, then you take a stack, use this parsing algorithm or parsing program on a particular input, okay, to scan that input. So basically, parsing program takes three inputs. What are they? You need a parsing table already should be constructed. It uses the stack, and the input buffer contains the input string which need to be scanned. And finally, it gives you output telling you that if that string belongs to a grammar, then it is successful. Finally, if you can generate the leftmost derivation, or if it is successful, then it gives you the, if that string is not there in the grammar, then it gives you the error. So this is overall picture of how this LL parsing program or algorithm works with the help of parsing table. But in the next few, we left with another 20-25 minutes time. So we'll see how to construct this parsing table. Okay. Then parsing program maybe we'll discuss in the next session. Okay. I think we'll not have that much time. So next, our next target is how to construct the parsing table. Okay, now see. Construction of parsing table, basically there are three steps. What is that? Step one is you remove left recursion and left factoring, if any. That means what? If the given context-free grammar contains left recursion, then you have to remove it. Or if the given grammar contains left factoring, then you have to remove it. That is step one. Because I already told you, that actually creates ambiguity. So step one, so that is the reason we discussed before it hand itself. So if the given grammar contains left recursion or left factoring, you remove it. That is step one. Step two is compute first and follow sets for variables. This is step two. We'll discuss now. Okay, how we compute first and follow sets. Then step three is apply the algorithm to construct the parsing table. Okay, there is some small algorithm. So use that algorithm, then you construct the parsing table. So there are three steps for what? For constructing parsing table. So please make a note. This is very, very important. And if you are really applying for the gate, there is a chance that you get a question on this. Okay, so you have to listen carefully. Okay. There is a chance that you will be asking. I already told you, unit 2, where the parsing thing is. All these, there is a chance that you get a one question on this area. Like starting with the context-free grammar, ambiguity, left recursion, left factoring, removing left recursion, removing left factoring. So from that topic, so this comes under, second phase, where there's a chance that you definitely get a one or two questions from this module. So listen carefully. Right. So what are the three steps? The construction of parsing table. First one is you remove left recursion or left factoring. Second step is for each variable you compute first and follow sets, and the third one is there is a small algorithm you apply and you construct a parsing table. Okay. Now let's take a problem straight away. Let us take this grammar. Now I want to construct a LL parsing table or a predictive parsing table for this grammar. Okay. So how we do this? What is step one? Step one is you have to remove left recursion or left factor. Now if you see here, this is left recursive grammar, and just now we discussed how you remove left recursion for the same grammar. Okay, so step one is remove left recursion, left factoring if any, and this is the equivalent grammar after removing left recursion. We have already discussed, right? Now let us see the step two. Now this is we didn't discuss what is this first and follow sets and how to compute first and follow sets for the grammar symbols. Now here, what are the grammar symbols? Grammar symbols means it could be a variable or terminal, but initially we need to compute first and follow sets basically for the variables. We need that. Now let us see algorithm for computing first of x. What is x? X is any grammar symbol. So see here, there are only three important rules for computing first of x. So how you compute first set? If x is the terminal, then first of x is x. That means let us say plus is there. What is first of plus? First of plus is plus. So if it is a terminal, then first of that is same. Okay, this rule is quite simple. Second one is, let us say x is not a terminal, it is a variable. And let us say variable, when I say variable, variable contains the productions. Let us say if x is a variable and let us say x has a production of the form x to epsilon. Then first of x contains epsilon. Okay, so if x to epsilon is a production for the x, then first of x you add epsilon to that set. But all the productions will not be of the form x to epsilon. So therefore, third rule. Let us say if we have x is a variable and x has a production of the form x to y1, y2, so on, yk. Now observe carefully. That means what? On the right hand side, there will be some substring alpha. And alpha, let's say there are k symbols in the alpha. The first symbol I am calling as y1. The second symbol I am calling as y2. And third symbol y3. So on, the kth symbol is yk. What is y1? Y1 could be a variable or terminal. What is y2? Y2 could be a variable or terminal. What is y3? Variable or terminal, so on. Okay. Now, in this case, how you find the first? This is important. The first two are very simple steps. You can easily understand. But step 3, you need to understand thoroughly. Okay. So, x2. So, in this case, first of x is basically we take as first of y1. That's all. First of x is first of y1. But suppose if first of y1 contains epsilon, first of y1 contains epsilon, in that case, even we construct first of y2 symbols also to the first of x. Okay, but suppose even first of y2 also contains epsilon, then we consider first of y3 also to the first of x symbols. Okay, but we don't include epsilon. So this will continue. If first of y3 also contains epsilon, then we go for next symbol. If first of yk minus 1 also contains epsilon, then we consider yk, the first of yk. If first of yk also contains epsilon, then only we add epsilon to the x. And in the process, we add all the symbols in this, okay, and so on. So please make a note, when we add epsilon in this case, we add epsilon if first of y1, first of y2, first of yk contains epsilon, then you add epsilon in the first of x. Okay, so these are the three rules. These are the three rules. Now let me give some case studies. Let us say I have a production A to B, C, D. Okay, let us say I already computed first of B. First of B is, let us say, small a and small b. And first of C also assume that I have already computed. Let's say it is small c and small d. And let's say first of D also I already computed, assume. Then let's say this is E comma F. So in this case, this is case 1. In this case, how you compute first of A? In this case, what is first of A? First of A is basically first of B. And what is first of B? It is A comma B. So therefore, first of A is first of B. So therefore, it is A comma B. That's all. So this is case 1. Now second case. Everything is as it is. A to, let's say, B, C, D is the production. And I have already computed. First of B, I already computed. But in this case, assume that it is A, B, epsilon. And I already computed first of C also. Let us say it is C comma D. And assume that I have already computed first of D. Let's say it is E comma F. Now in this case, what is first of A? In this case, the first of A is, it is basically first of B. So A comma B, but don't include epsilon now. Okay. Since first of B is containing epsilon, then I see first of C. First of C is C comma D, therefore I can add C comma D. So in this case, as per this production, first of A is A, B, C, D. So let me give you another clarity. Let's say case 3. Case 3 where let's say A to B, C, D is a production. Assume that before that, I have already computed first of B, which is A comma B comma epsilon. Assume that I already computed first of C, which is C comma D comma epsilon. And first of D also computed, assume. Then let's say this is E comma F. So in this case, what is, as per the definition, what is first of A? First of A is basically as per the definition, first of B. So therefore A comma B I add. But first of B is containing epsilon, therefore I take even, I consider first of C. First of C is C comma D. But first of C also containing epsilon, therefore I consider first of D. First of D is E comma F, I add. But please make a note, in this case epsilon will not come. So first of A is this. Now the fourth case. Case 4. So the production is A to B, C, D, and assume I computed first of B. First of B is A, B, epsilon. First of C also I computed, assume it is, let's say, C, D, epsilon, and assume even first of D also I computed. Let us say it is E, F, epsilon. In this case, what is first of A? So in this case, what is first of A? So first of A is basically first of B. So I add A comma B, but I don't include epsilon. Since first of B is containing epsilon, I take first of C also. It is C, D, but epsilon is there. Therefore, I even considered first of D. So I add E comma F. Even first of D also containing epsilon. So therefore, now I add epsilon. Hope now it is clear. Okay. So these are the different cases, right? Fine. Right. Now with that, let us see how we compute the first half variables. Okay. So after removing left recursion and left factoring, this is the grammar, right? This is the grammar after removing left recursion and left factoring, right? Right. Now what are the variables in this? E, right? E dash, T, T dash, and F. Okay. Now let us see how I compute first of E. So first of E is basically first of T as per this production, because E has only one production. So I should see first of T, but I don't know what is first of T. So to compute first of T, you consider T productions. So you come here, T, there is only one production, T to F T dash. So I should know first of T is nothing but first of F, but I don't know what is first of F. So let me compute first of F first. So first of F is what? As per this production, first of F is left parenthesis. Now as per this production, first of F is ID. Please make a note, ID is a single terminal. ID is a single terminal. Don't think that first of ID is I. ID is together is a one token. or one terminal. Okay. So as per this production, first of F is left parenthesis, and as per this, first of F is idle. So first of F is done. So since first of F is done, now let us see this. As per this, what is first of T? First of T is first of F, and first of F is left parenthesis ID. So therefore, first of T also left parenthesis ID. So once we computed first of T, now we consider first of E. First of E as per this is first of T. So therefore, first of E also left parenthesis ID. So therefore, see this. First of E is same as first of T. That is same as first of F, which is equivalent to left parenthesis and ID. Now let us see other variables. E dash. First of E dash. Now we consider this. As per this, first of E dash is first of plus. This is the first symbol. And first of plus is plus, because see the rules of first. What is that? Yeah. That is the rule, right? If X is the terminal, then first of X is X. Okay. So as per this, so first of E dash is plus. Okay. But and as per this, first of E dash is epsilon. Therefore, epsilon is there. Because I already told you, as per the rule 2, if X is a variable and if X contains production of the form X to epsilon, then you add epsilon in the first of X. Okay. Please see, refer rule 2 of first of X. Okay. So therefore, first of E dash is plus and epsilon. Now, how we compute first of T dash? So to compute first of T dash, you consider this production as well as this production. Okay, so as per this, first of T dash is star, and first of as per this, first of T dash is epsilon. Okay, so with this, we are done with computing first set. Okay, now let us see how we compute the follow set. Right. So these are the rules for computing follow sets. Okay, so follow of B, where B is a given grammar similar, B is a variable. Now there are 3 important rules to be noted. So listen carefully. Now this see, you place dollar in follow of S if S is a start variable. That means if B is a start variable, then follow of B contains dollar. If S is a start variable, then follow of S contains dollar. If E is a start variable, then follow of E contains. This is a blind rule. Okay, step 1. Okay, very basic point. And see second one. Please make a note, if you want to compute follow set for a variable, you have to search that variable on the right hand side of the production. That is the reason. See the rule. If there is a production of the form A2 alpha B beta, now we are talking about this B. Follow of B we are talking. Follow of the variable B. Okay. So if there is a production of the form alpha 2 A2 alpha B beta. So do not worry by seeing this alpha beta. So it means on the right hand side of some production. So here this is A production. On the right hand side of A production, you have B. Before B, there is some string alpha, which we don't bother. And after B, we have some string that is beta. Now, in this case, what is follow of B is, follow of B is first of beta. That is the rule. Okay, everything in first of beta, but except epsilon. Please make a note. Follow set will not contain epsilon. If you write epsilon in the follow set, means it is wrong. Okay, so B, the variable B is right hand side of some production, and after B you have beta, some string. Then in that case, follow of B is first of beta, but except epsilon. Okay, now as an extension, let us say you have production of this form A2 alpha B beta, or the production A2 alpha B beta where this beta is containing epsilon. First of beta is containing epsilon. So in that case, follow of B, in this case, follow of B is follow of A. Follow of B, how you do? You add everything in the follow of A, you add to follow of B. Suppose let us say you have this production. So in this case, fall of B is first of beta. And if suppose first of beta contains epsilon, then you don't consider that epsilon, but you consider other symbols of first of beta, and you also should consider all the symbols of fall of A. So please understand this too. Okay. So let me give some case studies to understand this. From this, let me create a new one. So let us take some case studies to understand these three rules. Yeah, anyhow, time is over at 12:25. I thought giving time to you. I'll stop here. We'll continue this follow set once again from the next Sunday. Any doubts now? The platform is giving for you for the doubts. Any doubts you can ask. Okay, whatever we discuss from that, you can ask any doubt. We'll discuss. If there is no doubt, maybe with the permission of your faculty, I'm just telling you, you can leave the session. But if you have doubts, please ask me. I'll wait here. If you have doubts, please ask me. There are 5 minutes left now. If you want, I can stay for another 10 minutes also. There is no issue. If you don't have any doubts, you can leave the session. Those who have doubts, you can stay and you can ask one by one. Any doubts? Anybody? Any faculties there? Yeah. Uday Kumar, are you there?
Sir, yes, sir,
Sir.
I'm here.
Yeah. I will stop now. I'll
Yes,
wait
sir,
for
yes, sir.
another 2 to 3 minutes.
Sir,
If they ask any doubts, we will clear.
Yes, sir. 1 minute.
Yeah.
Anyone have any doubts? Respond in chat box.
Yeah, you can type in the chat box also. I can see your doubts and we'll discuss. If you don't have doubts, you can leave. Is it fine with they or they should stay till end of 12:30? Yeah, Yashwant said no, sir. Okay, fine. Fine. Can anyone respond me like what is your branch in the chat box? All of you are CSE students only?
Sir,
Uday garu వీళ్ళంతా CSE students ఏనా?
sir.
వీళ్ళంతా CSE students ఏనా? Third year CSE students వీళ్ళు?
Yes, sir. CSA all branches, sir. CAI and CAID and cyber
అదేలేండి
security.
CSE and relevant branches, CSE aligned branches కదా.
Yes, sir. Yes, sir. Emerging branches.
ఈ KIET అంటే ఏంటి సార్ ఫుల్ ఫామ్?
Kakinada Institute of Engineering and Technology, sir.
ఇది
College.
Okay. This college from Kakinada.
Yes, sir.
Okay, okay. Shall we stop?
Yes, sir.
Okay, fine. If there is no
Thank
doubt.
you, sir.
Yeah,
Yes, sir.
fine.
Yes.
I'm leaving the session. If you want to talk to
Okay. Yeah, yes, sir. Yes, sir. Leave it, sir.